Hello, my name is Julia and I am your instructor of online MAT 210 class. Unfortunately, the live session today did not work, but I did create an amazing review for you. I looked through the quizzes, the exams we're going to have, and I definitely know what to show you to make sure that you can succeed on all of these. Please look over all of these examples, practice them by yourself. Make sure you can do it in a timing manner during the testing situation, and post your questions in the forum. That this way we can make up for the missed live session we were supposed to have today. Hope you will enjoy it and find it helpful. I'm pretty sure you will do a great job. Let's do it. Here are my notes for you. As you know, we covered 4 topics: limits, continuity, average rate of change, and instantaneous rate of change. Limits and continuity go together. Average rate of change and instantaneous rate of change, 2 topics that start introducing ideas of derivative. All these concepts are very important and take you in the world of differentiation, which have an unlimited number of applications in engineering, biology, and of course business. For example, if you want to find out what is the optimal number of units you need to sell in order to maximize your profit of the business you're building, you'll need to know instantaneous rate of change and differentiation. Or maybe when to sell the stocks, when is the optimal time to do that. All of these applications involve differentiation and rate of change. First, we introduced limits. As you remember, limit as x approaches to a of f of x exists when the left limit matches with the right limit. This makes sense if you look at the graph of the function, and as x approaches a on the x-axis, on the y-axis or f of x, the function approaches some kind of height. So if it approaches the same height from the left and from the right, you can claim that the limit exists. That makes sense. Even if the function is not defined at that point, limits still exist. Like in this case, I draw a hole, an example of the hole. Now, continuity. Continuity was a property. Let me carefully check that everything is going good. Yes. Continuity added one more property to limits, which we just defined. The continuity said that, if there's a hole, then the function is not continuous anymore. When there's a jump, the function is continuous anymore, and so on. Intuitively, we can explain continuity this way. If you put a pencil on a piece of paper, on the graph of the function, and you can go through the whole graph without taking a pencil out from the paper, then the function is continuous. Which means it should have no breaks, no holes, and no asymptotes, and so on. In this case, I'm drawing a hole, and to make sure that this function is continuous at a, I would like to fill in the hole. To fill in the hole, I want not only for limit to exist, but also to match with f of a, which is the value of the function at a. And that's how the definition of the continuity show up. Now we need to make sure that not only limit exists, but it also matches with the function of the value of the function, the point. Let's check all these ideas we taught you on the graph. Something like this you will see on the quizzes and exams in this class. So it's very nice a way to practice before quiz and exam. Here's the graph of the function, and I want you to find all the points of discontinuity and also define a domain. And also you have to justify everything. So of course you can always say, I can see there is a jump or there is a gap, which intuitively right, but mathematically speaking, you have to justify. Let's start with -10. Here it is, -10. Definitely something is going on in -10, so I want to check this point. You see, nothing is interesting happening in -12 or -10.5, nothing really happening in -5. So it makes sense to check only points which visually look like discontinuities. To see if the function is continuous at -10, we need to check if the limit exists. So I wrote down limit for you of f of x as x approaches -10. To check that this limit exists, you need to check if the left limit exists, right limit exists, and they are the same. Then limit exists. Make sense? So reviewing how to do it. Look at the blue color on the x-axis. When I am approaching on the x-axis, -10 from the left, that's the first limit, you need to look at the graph of the function over there. What height do I approach? While x on the x-axis approaches -10, the height of the function, of the graph of the function, approaches 2 from the left. Now, same idea from the right. When x approaches -10 from the right on the x-axis, what my y does, or f of x, it approaches some kind of height. Let's see what height is this? 2. So it means I can write down they both equal 2. And then I can say thus, limit as x approaches 10 of f of x exists, and it is 2. So this is the first conclusion. But there's a second part of the definition of continuity. I also need to check what is happening at f of -10. If this is 2 as well, then the function is continuous at -10. Let's see what is happening at f of -10. F of -10 is not defined. I can say not defined. Thus, f at -10 is not continuous, and it has a hole, which is a removable discontinuity, which technically speaking we can fix, but we don't have to. So that's the first point. Now, what do you want to check after this? Something is definitely happening at -3. Looks like a jump. Let's check that this is the case. 2. Limit as x approaches -3 from the left, limit of the function f of x, as x approaches -3 from the right, from the left, let's use different color, x approaches -3 from the left, f of x approaches from the left this height over here. Let's check what the height is. It's 1. So from the left it is 1. From the right, when I'm approaching -3 on the x-axis, on the graph of the function f of x approaches a different height this time. This height is -4. -4. So I can say that they do not match, left limit do not match with the right limit. Thus, limit as x approaches -3 of f of x does not exist. We can also say, since both numbers are finite, that actually there is a jump, discontinuity happening at this point. Also, since the first part of the definition of continuity already failed, then we can say that f of -3 is not continuous as well. It has a jump. You don't have to check if f of x exists, and actually f of -3 is defined and it is 1. Doesn't matter. It still has discontinuity. And one more, let's check what's happening at 4. At 4 over here, 3. Limit as x approaches 4 from the left, limit as x approaches 4 from the right. Let's make it faster this time. From the left, I will use yellow color here. Where do I go from the left? I'm approaching height -2, in this case, equals -2. From the right, it seems like I'm going to plus infinity forever up. Plus infinity. So I can say again, thus, limit as x approaches 4, f of x, let's make it more visual, -2 from the left, plus infinity from the right, does not exist. And in this case, because one of the limits, one of the side limits is infinite, we can say that this is infinite discontinuity. Jumps and infinite discontinuities cannot be fixed, so they are called not removable discontinuities. Also, the first part of the definition of the continuous function is failed, so you can say that f of 4 is not continuous. Careful look at the graph everywhere else. Do you see anything else? What is happening here at 10? Seems like left limit matches with right limit and the function is defined there, so it's continuous. It's continuous at every other point, so we don't have to check all of these points, and we can. There are infinitely many points over there. So now we can claim what are the interests of continuity here, or we can say that the function, or basically domain, or if we're gonna ask you on the test, define interests of continuity, I will start from negative infinity from the left, right? Here it is, negative infinity. Then I would say over here, something happens at negative 10. We said that negative 10 is not continuous. Negative 10. Should we include negative 10? No, because at negative 10 is not defined. Union symbol. Then negative 10, not included again. Now it seems like when I'm approaching negative 3 from the left, the point here is filled in, you see? So it means I can include negative 3 with a bracket. But to show that there's discontinuity there, I will make union, exclude negative 3 from the right, because from the right there is a hole over here. Make sense? Finally, from negative 3 to what number? 4. 4, I'm not including 4 because there is a hole. And then union, something happens at 4, we already checked that it is infinite discontinuity, and then 2 plus infinity. We can even make some notes for yourself if you want. There is a hole over here, there's a jump, and there's a vertical asymptote at 4. VA, vertical asymptote, or infinite discontinuity. And that's what we're going to do in this case. That was example number 1. One more example. What if I don't give you the graph of the function? Example 2. But I give you instead equations. So I have 4 plus x when x is less than 1, and then 7x plus 10 when x is greater than 1. This is how you should see, this is how I usually explain it to students, and I think they're getting it in this way. Basically, function here is piecewise function. Piecewise function is the function that's made up of pieces. You might think it's actually not a very popular thing, but actually all our utilities are piecewise functions. Today you're paying $45 per internet, tomorrow it jumped to $75, then it dropped down by a discount to $35. So most of our utilities are actually piecewise functions. This function has 2 rules. It might be 15 rules, 25 rules, and so on, and it really depends on the point. So usually I call them rule number 1 and rule number 2. And then you choose which rule to use, depending on how you approach x. So if I'm approaching 1 from the left, I'm choosing the first rule, because when I'm approaching x from the left, when I'm approaching 1 from the left, x is always less than 1. When I'm approaching 1 from the right, this is rule number 2, because then x is greater than 1. And this is how you know. So for this problem, we want you to find side limits. Find side limits. Well, let's do the first limit is as x approaches 1 from the left, f of x, and the second one, x approaches 1 from the right, f of x. Nice. And now you know, based on my explanation, now I think you're getting it. The one from the left is not always the first one, but in this case you have to think about it. So approaching from the left, this is how you can imagine it. 1, approaching from the left means I need to choose rule number 1. Rule number 1 is over here. So I will use this limit, and I will calculate limit as x approaches as x approaches 1 from the left for 4 plus x. Based on the properties, you can just plug your 1 here. You can completely ignore a negative sign. This minus sign here just helps you to choose which rule do you use for this case. So I'm plugging 4 plus 1 and it becomes 5. And this is the answer, which means when x approaches 1 from the left, f of x approaches 5. It's a height of the output. Same idea from the right. From the right, we're going to choose second level. For the second level, we're plugging everything into 7x plus 10. We're plugging 1, even though it's plus, you're ignoring it, it becomes 7 plus 10, which is 17. This is how you know how to work with without the graph of the function. And then you can see, okay, these two do not match, and you can say then it means that limit as x approaches 1, f of x does not exist. And again, we have a jump, discontinuity here. Basically, it's literally the function jumped, the output of the function, the height, jumped from 5 to 17 when it was approaching 1 from the left and from the right. Hope now that makes it more understandable. After this, a good example. Finally, after this, we were teaching you how to solve limits, any kind of limits. And I usually explain it using examples and steps. When we give you a limit and we ask you to calculate the limit at 5, 10, -1, that's what you did for your homework, I usually teach it with these funny steps. Step 1. When I give you the limit, please don't overthink it right away. Maybe you can just plug in, I will do like this, steps. 1. Maybe you can just plug in the number like I did over here. I plugged 1 and it was 4 plus 1. There is no discontinuity here, no division by 0, no negative numbers. So maybe everything is fine. Step 2. When you plug this 1 or any other number, and then you end up to have 0 in denominator or some kind of problem, then it's time to do some action, some kind of simplification. So step 2, simplify. Plug in, simplify if needed, and what kind of ways do we use to simplify? We have different formulas we needed to know. For example, x plus or minus y squared, that's sum or difference, square of sum or difference. X squared plus or minus 2xy plus y squared, you need to know this. We definitely had difference of squares many times for those standard examples, and the secret is you're probably going to have it on the quiz and exam again, so definitely learn these, and so on and so on. Sometimes you have roots, remember, when you need to have a conjugate, multiply by conjugate, those guys work too. If you have sine cosines, simplify these as well. When you're done simplifying, oh, maybe factor, so let's do this, and remember, sometimes just factoring works. Factoring might work. When you're done with these steps, plugging in again. Plug in again. And maybe now everything is fine. The whole goal of these steps is basically to get rid of the troublemaker. There's usually some kind of troublemaker in the denominator or a square root. By multiplying square root by 1 more square root, you get rid of the denominator. By factoring and dividing by the denominator, you getting rid of the troublemaker in the denominator. That is very clear from these examples I'm going to show you, and you saw them in your homework many times. For example, a limit of x squared plus 2x x cubed plus 2x squared minus 1 all over x plus 1, and x goes to 2. You see, I notice students sometimes overthink and they start factoring out right away, figuring out something like full square and so on. No, always do step 1 first. Let's plug 2, maybe everything is fine. 2 plus 1, that's completely okay, so you just need to calculate everything carefully. I will have 2 cubed, that's 8, minus 2 cubed again, that's 8, minus 1. So the answer is negative 1/3. Done. How fast is that? Then of course, probably you will see on the quiz and the test some kind of cases when it's not that straightforward anymore, and you will have to perform step number 2, which means simplify something or get rid of the troublemaker. Let's see. X equals 1. I'm plugging 1 in denominator. We are getting 0. So you have to get rid of this bad guy, x minus 1, to be able to move on. Then move on to the step 2, simplify. What formulas do you see from the list which you can use? I see the difference of squares. X minus 1, x plus 1, have this. Since x is never 1, do you know why? X cannot be 1 because x approaches 1 as close as we want. Maybe it's 0.9999999, but it's never going to be 1. That's the idea of the limit. We can approach infinity as close as we want, but it's never going to reach infinity. We can approach 1 as close as we want, but it's never going to be 1. So x minus 1 never going to be 0. This is important because you can cancel out only something non-zero. So now you're having x plus 1, plug your 1, and it becomes 1 plus 1, which is 2. Done. Not too bad. One more. Last one. X approaches 3, and I will have x squared minus. Oh, that was a weird one, I remember. Yeah, that's a different one. There was one example I was hesitating to put in. X minus 1, x squared plus x minus 2. Again, plugging in 1 doesn't work, so you have to do something. I don't see how to factor anything here. Square of some difference, no. Difference of squares, no. Then learn what the sum of square, difference of square, or what does it mean to find roots of quadratic equation. In this case, we're working with x minus 1 and x plus 2, x minus 1. Make sure you can do this. Make sure you can convert this quadratic equation into the product of the difference of roots here. Then same idea. I can cancel out the troublemaker, and I end up to be 1 plus 2, which is 3. Done. Not too bad. After this, do you guys remember that we introduced to you infinite limits? Infinite limits. Did you like this topic? I don't know, my students usually like it because working with infinities is fun. And this is how I'm gonna fast introduce you this idea, to review it again. X cubed plus x minus 11 all over x squared plus 1. You see there's no 0 in the denominator. What's the problem? Well, I want to see what is happening in the long run with this function. In the long run means at plus or minus infinity. Very reasonable question, because sometimes you want to see what is happening in the future. For example, we want to see how the universe is expanding. How come we can predict how fast does it grow without ever waiting for millions of years? Because we use limits. We use limits at infinity. That's how important this basic idea. So this is the idea. I teach it this way, although you saw it in the book in the standard way. Find the highest, the x with the highest exponent in the numerator and divide everything by that. I do it this way. Find the leader in the numerator. The leader is the x with the highest exponent. The leader here is x cubed. Find the leader to the denominator, x squared. Compare the speeds at infinity. The one that's faster wins. If the one who wins is at the top of the fraction, then the top explodes faster than the bottom, and the total answer is infinity. You should see it as a competition of two exploding universes. One is exploding and the other one is exploding. If whatever is exploding in the denominator explodes faster, it means everything shrinks really, really fast, and the answer is 0. If the one that explodes in the numerator is faster, then it's much faster than the shrinking process at the bottom, so everything expands faster and goes to infinity. Basically, you can imagine if you have a black hole which shrinks everything into the center of the black hole with a really, really high speed, But then you have a huge explosion in the middle with a black hole. Which one is going to win? The explosion will explode and everything stretches, or the shrinking process is gonna be faster and stronger and everything shrinks. You know, that's the idea. Very interesting explanation, I think, and usually people are getting it. So, just like I said, what happens if the guy at the bottom wins? So say it's 8x to the 7 minus 10x, and at the bottom say it's like plus a million or whatever. You still follow the same logic. Find the leader at the top, that's x. The leader of the bottom is 8x to the 7. Which one is faster? 8x to the 7 is faster. The other guys don't matter. They just follow the leader. That's why I call it a leader. It's like imagining the whole universe versus one planet. Universe has a speed 8x to the 7, and there's like one planet which is moving behind. The planet will follow the universe. That's how you can imagine it. So, what I'm talking here about is that there's some kind of infinity explodes in the denominator. So you start dividing by huge numbers. First you divide by 8, then 100, a million, 3 millions, 5 billion. You divide by huge numbers. And what happens when you divide by the biggest number, like infinity? Well, the answer is the smallest number, What's the smallest number, 0. Because numerically speaking, you can understand that numbers become smaller and smaller. What happens when speeds are the same? X goes to infinity, and you have 3x to the 5 minus 7x plus 10, then 13x to the 5 plus 10x squared minus 1000. What happens here? Find the leader at the top, find the leader at the bottom, and compare the speeds. If speeds are the same, you can actually write this down as a limit. X goes to infinity, 3x to the 5 over 13x to the 5. Since all other parts following the leader, in the long run, they will behave like leaders, so you can just completely ignore those tails. Well, x to the 5 simplifies, and the answer becomes 3 over 13. That makes sense. If the explosion at the bottom and the top have the same rates, then the answer will be the ratio of the leading coefficients. Basically, the first one explodes with the rate 3, the second one explodes with the rate 13, so how fast the total explodes with the rate 3 over 13. Done. Hopefully now you can successfully do these problems on a test. After this, we actually were done. All those infinite limits. We did introduce some limits at infinities. When you remember, we had the vertical, horizontal asymptotes, but I think I already introduced them here in the graph. If one of the numbers is infinity, when you approach the point from the left and from the right, that usually indicates vertical asymptote over here. And it can go plus minus infinity, up and down, from the left and from the right. If you want to know how to find horizontal asymptote, then you need to set the limit to go to infinity. Let me just review it briefly. VA, how to find VA? Look for zeros at the denominator. So, for example, 1 over x plus 1 has a vertical, VA is a vertical asymptote at x equals minus 1. How do I know? Check left limit and right limit. You'll get infinities for both cases. Now, how about horizontal asymptotes? For horizontal asymptotes, find infinite limit. Send your x go really, really far to the right or really, really far to the left and see what's going to happen. If the answer is infinity, if the answer is some kind of number, let's call it a, that indicates that the graph of the function stuck at some number. It looks like this. For example, we want to see how many rabbits there are in the Yellowstone Park. And we started with some kind of population of rabbits and let's keep growing, keep growing. Do you really believe they will infinitely grow? No. At some point the resources will be shrinking. They will be eating too much food and so on. That's why there are always some kind of resources restriction for all population models. So at some point you will see it will decrease and maybe stuck at some number. Maybe it will never reach it, but it will stuck at some number. And that's how we know how many potential population of rabbits or zebrafish or lions do we have. If, as x goes to infinity, f of x approaches some kind of number, that's called a, that represents then y equals a, do you see it's on the y-axis, so it's y equals a, is horizontal asymptote, versus vertical asymptote is x equals something. Remember this difference. After this, we started introducing average rate of change and instantaneous rate of change. So that's already topic 3 and 4. Average rate of change, ARC. It's not very common notation actually, but just convenient to write down. Remember the formulas: f of x2 minus f of x1 all over x2 minus x1, average rate of change. Well, basically change in output is your y-axis. I don't want to call it y because it may be anything else, like gravitational forces and so on, over change in input. That's the idea. That's the idea here. There was one more notation. Oh, and then we're gonna ask you to find the average rate of change. Of course, find average rate of change using this and that. Using a step size or not step size. But I just want to point out before we move on to the example, how did we jump from this to topic number 4, which was instantaneous rate of change. Instantaneous rate of change. We used just rate of change, and then we said, you know what, I don't like having these differences. Can a difference be close to 0? This difference over here. Because sometimes you need change to be very small. A very funny example is, for example, you're observing Clark Kent, which is Superman, spoiler alert, sitting on a chair. And he's wearing a suit and, like normal working suit for the office, and making a photo for an office purposes. You making a photo and say every click of your photo camera is 0.02 seconds. And what you see in front of you is just a sitting person. He's sitting there and smiling. But between those clicks, Clark Kent changes into Superman, flies in somewhere, saves a person, comes back and sits down, changes back and sits down for the next click. That's possible. For you, this person is sitting and the average rate of change will be 0 because there's no speed. But for that person, he's so smart, so fast, that his speed is really, really high, and average rate of change is actually very high, not 0. What's the problem here? The problem is with technology. If this change is not small enough, like 0.02 seconds is not good enough to catch Superman flying away and coming back, then you want to shrink it and make it smaller. So that's how usually it's a fun way to introduce this whole idea of instantaneous rate of change. Can I make sure that this is small? And let's may say not just small, but small enough. Small enough for any concrete purpose. For example, I want the change to be small enough to capture the cell division or a cancel cell, a mutation, and so on. To use this, to catch this, we use instantaneous rate of change. How to make something as small as I want, to make it infinitely small. Those words are familiar to you. Those words indicate limits. Limits, take the bottom and make sure that the bottom, so in this case x2, goes to x1 as small as possible. Then, of course, the top will be changing as well because they depend on each other. That's what you call instantaneous rate of change. The formula you probably remember is using h. If I'm calling h to be a step size or the change, like how fast the camera clicks between shots. So h shrinks to 0. Then f, a plus h, that's the step away from a, the original moment in time or place, minus the original moment. That's instantaneous rate of change over here. Good. Now, let's do a couple of examples. Example 1. The first example is about those application problems, remember? I was choosing which one to show you, but basically they're more or less the same. So practice this and you should be fine. An object moves with some kind of equation. So we're gonna give you an equation for some kind of move. And in this case, it's displacement, or basically distance. Displacement is distance with the direction. And let's say it's a cubic function, t cubed plus 30t plus 100. Find average rate of change. Find average rate of change of the position function, of the position for the time period, and we give you time period from t equals to 1 and t equals 5. That's like 5 seconds, for example, of making a video, or maybe this is a flight of the plane trajectory. And we want to know the average rate of change of the plane that's flying. Then just remember solution. Remember the formula. You have distance change at the top, distance change over time change, because time is my input and distance is the output. You see, time is the input, distance is the output, so it makes sense. It's f over x, change in f over change in x. In this case, not f, it's called s, doesn't matter. So we're going to have s of 5, always do the second one first. We always find like how far did I walk from home to Walmart. I always do distance from Walmart minus distance of home, right? This kind of makes sense. You always do the last point minus the original point. S of 1, and the bottom I have 5 minus 1. Change in output over change in input. Also, just to point out that there was a miles in the numerator and hours in the denominator. Carefully plug in all those values into your function. The top becomes, plug everything everywhere 5. 5 cubed plus 30 times 5 plus 100 minus 1 cubed minus 30 minus 100. Don't forget to distribute the negative sign. If you're afraid to mess up, I would recommend you to put minus and then brackets and then distribute later. The bottom is 4. 5 minus 1 is 4. Carefully calculate everything. You will have 375 minus 171 over 4, which is 61. Do you know 61 what? Miles per hour. So it makes sense. If I give you distance with a given time, average rate of change will be 61 miles per hour. Miles per hour. And this is how you see these change the speed limit when you drive, miles per hour. That's the average rate of change. Now, how about the step size h? Do you remember those problems with step size h? I think sometimes they're confusing. So let me review these. So how to do the same thing, kind of, but using h as a step size. You will see this idea that h is a step size actually in many places, especially in business. It's very useful, and in coding, if you like coding, you will see this idea everywhere, in Java and C++ and Python, whatever. Here's a function. I give you a function 60x minus 3x squared. And I ask you to calculate the average rate of change. But in this case, I give you near a 0.3 over the given interval. And interval will be a, and then a plus a step size. So it's 3 and then 3 plus h. And then I tell you how far should you step away. you will step away by 0.1, then you will step away by 0.01, then you will step away by 0.001. Do you know what I'm doing here? It's basically this example with Superman. How small the step size of the camera should be, how fast the clicks should be, 0.01 or 0.001 or 0.001. The smaller the better. That's why in perfect model, h goes to 0. What's the idea here? We want to estimate. So let's do A. It doesn't matter, it will be a table. Estimate the instantaneous rate of change. So first find average rate of change, and then you will see a pattern. If you see a pattern, you can estimate the instantaneous rate of change. We're going to use the formula here. Solution. We're going to use f, a plus the step size, minus f of original point, a, over h. And we can start plugging in at least 3. 3 is fixed, right? So a is fixed, it's 3, and then h is changing. So every time we're going to have 3 plus h minus f of 3 over h. But f of 3, that means I need to plug 3 over here. So x is 3 over here, and also plugging x equals 3 plus h. That's the one that the students get confused all the time. Let's do it in the form of a little table. You don't have to draw a table, but I think it's nice ways to organize everything. A is 3 all the time. H is changing. First is 0.1. You will have, for 0.1, f of 3 plus 0.1 minus f of 3 all over 0.1. Well, 3 plus 0.1 is 3.1, so you can actually skip that step and write it immediately, just f of 3.1. To be faster, plug 3.1 in your function, and it becomes 60 times 3.1 minus 3 times 3.1 squared. That's the first part. Minus, put brackets, not to make a mistake, and then your original function at 3, which is 60 times 3 minus 3 times 3 squared. Do you know where I'm plugging everything? I'm plugging everything into this colorful box over here, rainbow box. So I'm plugging here first 3.1, and then I'm plugging 3 everywhere. And the difference should be small, because 3 and 3.1 don't have a lot of difference. It's just a 0.1 difference. And then dividing by this difference, by 0.1. The answer is 41.70. Next one, h equals 0.01. Repeat the step. F of, you're going to have 3.01. Make sense? Because it's 3 plus 0.01. Minus f of 3 all over 0.01. Carefully plug it in, and you'll get 41 times 97. You see the pattern is definitely close to 41 or something like that. One more. The smaller the interval, the more precise your calculations are, but it's hard to perform them. 3001 minus f of 3 all over 0.001. If you calculate, you can trust me, but you can calculate by yourself. It's going to be 41.997. Interesting. So note number 1, those are average rate of changes with different age, right? With different age. But you can see that it's all getting very close to 42. That's approximation of instantaneous rate of change. Instantaneous rate of change. How did we approximate? Finding as many average rate of changes as possible with the smaller and smaller step sizes. So Ideal situation is when h goes to 0, and that's why h goes to 0 includes in the formula, so I don't have to plug 0.0001 all the time. Oh, missed 0. Nice. And in computer you actually plug. Computer will tell you when it's too much, because computer can crash due to lack of memory. So definitely I think now you can perform these calculations on the quiz if you see those problems. Now, applications in business. Remember those problems with the price of stocks and stocks prices and so on? So let's do that. Applications. Applications in business. Examples. Let me put this like here. If we give you a function which represents price of the stock in the stock market, it's a price of the stock, and we say it's like a stock for TVs, whatever, electricity, I don't know, anything, doesn't matter, for t's day. So say 5th of January, so it's going to be 5th day of January. And I will tell you some kind of information. Data was collected, and I can say that the stock price was originally $300. You can see I always put $sign after the number. That's the Russian style, so you don't have to. You can put it before the number. And then the price dropped. And then we know when. That's the most important. We know that on January 5, that's going to be important because then you know what T is. T is 5. January 5, it dropped. It dropped by $40. Then find limit P of T when T approaches this day when the price dropped, when T approaches 5. Solution. Let's check what happened before January 5. So it means we're basically looking at the limit from the left. When T approaches 5 from the left, P of T, that means before January 5. Before January 5, it was $300. Make sense? Now let's find what's happening on the right. T approaches 5 from the right. P of T is, it dropped by $40, so now it's $260. Make sense? Then you can say, well, those are not the same. So you can say that the limit when T approaches this day 5, P of T doesn't exist. Doesn't exist. Those problems are not very hard. They're just a lot of reading, and I would recommend you to look for keywords. I give you a function and I call the price of a stock market. Then I say T will represent the time, the day in the calendar. Then I say the original price was some kind of number. Then I say the date was important, and this date it dropped or increased. That's important. It dropped by how much? $40. Now you can make these calculations. Originally it was 300, then it became 260. Since it's not the same, limit at P of T does not exist as T approaches 5. Not too bad. Finally, we introduced definition of the derivative. Do you guys like this chapter or not? I promise you it will get easier after this. I literally promise you. This is one of the last hard chapters, and then students love what happens after definition of the derivative. It becomes straightforward, it's just a lot of practice, and you succeed really fast. It's good. This is the last one you have to struggle with, which is definition of derivative. Basically, instantaneous rate of change led us to the definition of the derivative. Derivative is a function which is defined in many ways. One of the ways is, let me make it nicer, limit as h goes to 0, the bottom shrinks to 0, the top changes accordingly, and this gives you rate of change. Which kind of rate? Instantaneous rate of change. Definition of derivative. I usually give my students, let me make a box first, Put in a box, it's important. We're gonna ask you this. I usually give my students some keywords. Keywords, if you see them, you know they're asking you to find derivative. So you see if they ask you to find instantaneous rate of change, then it means they want you to find derivative. If they want you to find slope, means derivative. If they want you to find speed or velocity, find a derivative, which means differentiate. If they want you to find, if you see some phrase in the problem which says how fast, find the derivative. What else? Sometimes you see per. This like find how many miles I traveled per hour. That still means we want you to differentiate how fast. And of course, for business students, we're gonna use a lot of marginals. Find marginal of the cost function, profit function, revenue function. Immediately you see this, it's supposed to trigger you. They want you to find a derivative. That's it. Very nice. When I give this list to students, they do much better on the exams. Because exams are timed, I understand that this is a stressful situation for everyone. You see those keywords, at least you know how to do step 1. Step 1, differentiate if you see rate of change, marginal, how fast, instantaneous rate of change, tangent line, and so on. Slope, you know it's m, f prime of x or t or whatever. I will do a at the given point, a. Yes. Actually, I did not miss anything. That's all the good keywords. And this is just, it actually will be very helpful for 210 and 211. You'll see this a lot, so maybe write it down somewhere, have a good note somewhere. Now, and finally we ask you, that's going to be my last list of examples. Find the derivative of the function f of x, which is 3x squared. Find f prime of x using definition. Using definition of the derivative. And that's very important for the exams in my classes when they don't follow this rule, they don't use definition. When I say you to use definition, we give 0 points. I should tell you, it's actually an American system that teaches it this way. In Europe and in Asia, you can ask students, we don't really do it that much. Yes, we introduce a definition in this box. We're like, okay, we know what it means and stuff like that. And then we immediately jump into formulas, which you will see this week. And those are easy, straightforward formulas. Why do we need to push students to perform definition all the time? I know the derivative of 3x squared is 6x. That's it. Anyhow, I should tell you, we're gonna only ask you to do it a couple times, and then we will never ask you to do it again. So struggle for a little bit, and it's not that bad after all. Just a little bit of annoying writing. Solution. So f prime, by the definition, is a limit. As h goes to 0, put h at the bottom and don't touch it. Then at the top, I will have 3, and then you know what to do. Plug x plus h. I will do function first, just to remind you. F of x plus h minus f of x, as h goes to 0. Well, my function is 3x squared, so don't forget to write limit again. H goes to 0, h is in the denominator, and now everywhere you see x, you need to plug x plus h. Basically copy paste, or if you know what I'm talking about, you find and replace. There's a command like this, find and replace. Everywhere you see x, put x plus h, saving all the exponents, negative, positive signs, and so on. So I have 3x plus h squared, that's the first piece, minus the original function, which is just 3x. And now we're playing with limits just like we did before at the beginning of this review and at the beginning of the first chapter. Plug your h equals 0. Doesn't work. I'm plugging in. I have division by 0 in denominator. So step 2, simplify. I see some formulas to recognize. There's a square of sum. Usually to save time, I will teach you how to be fast on the exam. I take a pencil or different color And this piece, I'm doing it separately. So I'm doing it small font and write down here x squared plus 2xh plus h squared. Done. Then it saves me writing because now I can distribute right away. 3. I'm multiplying all those pieces by 3. So it becomes 3x squared plus 2, well 3 times 2 is 6, let's keep this step. 6xh plus 3h squared. That's the first piece. Minus, maybe put parentheses for the second piece in case you need to distribute negative sign. 3x squared. Now you still have h in the denominator, but you hope that something will go away, and something should go away. 3x squared and minus 3x squared. Whatever stays now has h in it everywhere. I have h here, and h in denominator. The whole idea of finding derivative by the definition is to get rid of the bad guy at the bottom, so you want to factor out this h. Don't forget limits still everywhere. You have h at the top, factor it out. 6x plus 3h over h. Since h will never be 0, like I mentioned before, you can cancel it out, and you end up to be with a limit h goes to 0, 6x plus 3h. Now be careful, where do you plug your 0? Limit tells you where to plug. Where you see h, plug 0. H only, not x. For this limit, x is a constant and h is a variable. So you'll have 6x, and this is the answer. Based on the simple formulas, rules, you actually know that derivative of 3x is 6x. So for you to know the original function, 3x squared, for example, it's a distance, and when you ask how fast it is, you have the answer is 6x fast. That's the idea of the derivative. It shows you the speed. This was A. Find the derivative in general. B. Find f prime at, say, 7. Do you know how to do that? Don't repeat the whole process. Take the result and plug in 7. You'll get 42. Those are all notes I wanted to show you, and this is actually good enough to do really well on the first quiz. Really, really well. So just make sure you look over everything I showed you here, practice these questions again and again, maybe remember some keywords to be faster, maybe catch yourself doing some calculation mistakes. Practice this plugging in h pieces to be fast in these. Practice to use your calculator. Don't forget to put parentheses or brackets in order not to make mistakes with negative signs, and so on and so on. Not so many things, as you can see. It's almost done. I'm keep scrolling, and here's the beginning. So practice those things, and I am sure you can do 100% on the first quiz, and many of these things will show up on the final exam. I already checked, and I just tell you the truth. Many of the things are very important, so we definitely want to put them to the final exam. But I think for now this is good, and I hope this was helpful. Good luck on the quiz and your studies. Please post more questions in the forum, and I will see you around during the next review session in the month, I think. Good luck. You will do great.